Great. So we are going to measure the spring constant two different ways. The first way we're going to measure the spring constant is through Hooke's law. Basically, what we're going to do is we're going to take a spring here. Make sure that the more tightly coiled, let me take this off for a second. The more tightly coiled side of the spring is at the top, and the less coiled is at the bottom. Because it does have a slightly variable spring constant, but the fact that the top of the spring is supporting the weight of the bottom of the spring tries to get evened out by the fact that this coil is a little bit tighter up here and a little bit looser down here. So it gives roughly a constant spring constant, again, because the weight down, the spring up here has to support the weight down here, whereas the spring down here doesn't have any weight to support it when it's just hanging by itself. Okay, so what we're going to do is we're going to take a hanger, and we're going to just put the 50-gram hanger on there, and then we're going to measure the position of that hanger. I tell students to always go from the bottom of the hanger there, so approximately that point right there. Looks like about 41 centimeters, somewhere around 41 centimeters. The actual number is not important. What's important is how much this stretches after we add weight to it, because every time we add a little bit of weight, that weight is going to pull on the spring and stretch it a certain amount. So if we always add, say for example, 50 grams, we're always adding the same amount of additional weight. So if the spring remains elastic, then because of the linear restoring force, it should always stretch by the same amount. So if we're always adding 50 grams, it should always stretch by however many centimeters, 2 centimeters, 3 centimeters, whatever. So here's an example of what the students would do. They first measure the position of the bottom of the hanger when it's just there's no additional weight on it. The hanger itself is 50 grams, but we can set that as our 0 there. And then what they'll do is they'll take an additional amount of weight, go up by 50 grams or 100 grams or whatever. So an additional 50 grams will stretch, and then stretches a certain amount. They'll measure the second position, and the difference will be the delta x. And then they can plug it into the Hooke's law to solve for k. Well, they could plug it into Hooke's law, and that would allow them to determine k. But first, what they should do is they should just keep adding 50-gram weights and measuring the position after each successive weight is added. And once they have five or more data points, what they're going to do is they're going to graph the weight versus the position, the weight on the vertical axis versus the position on the x-axis. And that will allow them to, the slope of that line should be equal to k. From Hooke's law, F equals k delta x, where we would plot F as the weight, right, which is the mass times gravitational acceleration on the vertical axis. On the horizontal axis, they'll measure the total delta x from this, from the bottom of the hanger there at each successive interval. Once they have 5 data points, they should be linear, and they can take the slope of that line, and that line should give them the spring constant via Hooke's law.
Okay.